In this presentation, we introduce complex numbers. The complex number system is an extension of the real number system. It unifies the mathematical number system and explains many mathematical phenomena. We introduce a number I equal to the square root of minus 1, defined to satisfy the equation x squared is minus 1. Of course, if I squared is minus 1, then minus I also satisfies this equation. So we now have two solutions to the equation x squared equals minus 1. They are I and minus I. The complex numbers are defined as all numbers of the form a plus bi, where a and b are real numbers. So we'll write the complex numbers as this set of all numbers of the form a plus bi, a and b from the reals. A complex number of the form a plus bi is said to have a real part a and an imaginary part b. Any number can be written as a complex number in the form a plus bi. 3i is 0 plus 3i and has real part 0 and is said to be purely imaginary. But the number 5 is 5 plus 0i. It has imaginary part 0 and is real. The real numbers then are a subset of the complex numbers. The conjugate of a complex number, z equals a plus bi, is created by changing the sign on the imaginary part, getting z bar, which is a minus bi. So the conjugate of a plus bi is a minus bi. We change the sign on the imaginary part. Thus the conjugate of 2 plus I is 2 minus I. The conjugate of the square root of 3 minus pi I is the square root of 3 plus pi I. And the conjugate of I is just minus I. The conjugate of the real number 5 is merely 5. The conjugate of any real number is just the real number itself. The nicest version of the fundamental theorem of algebra says that every polynomial of degree n has exactly n zeros. If the degree is n, the number of zeros is exactly n. Surely this is not quite true, is it? Consider this function, x squared minus 1, the function x squared, and the function x squared plus 1. We can graph these functions in the plane, and f is in green at the bottom, g is in blue a little further up, and h is in red. Here they are again. It's obvious that the quadratic graphed in green, f of x is x squared minus 1, has two zeros at 1 and minus 1. In other words, x squared minus 1 factors into x minus 1 times x plus 1. If we move this green parabola up one unit, we get the graph in blue, g of x equals x squared. Now the two real zeros at minus 1 and 1 have merged into a single x-intercept at the origin. We claim that g of x equals x squared still has two zeros if we're willing to count multiplicities. And this makes some sense because we can write x squared as x minus 0 times x minus 0. So we can think of 0 as being a root twice. Here's a picture again. The function x squared minus 1 has two zeros and factors into x minus 1 times x plus 1. The function x squared has two zeros, both of them at 0. What if we move the parabola up one more step to create the one in red, looking at the function x squared plus 1? Suddenly now there are no real zeros. The parabola in red never touches the real line, the x-axis. Have we lost our two solutions? Can we fix this? Can we somehow make sure that this quadratic polynomial x squared plus 1 still has two zeros? Well, this is where complex numbers come into play. Algebraically, x squared plus 1 doesn't have any real zero because this would require that x squared plus 1 equals 0, or that x squared is minus 1. And if we square any positive real number, the result is always positive. So there's no way we could take a real number x and square it and get a negative number. But if we use imaginary numbers, then the equation x squared plus 1 equals 0 has two zeros, but they're imaginary, I and minus I. The quadratic x squared plus 1 now factors as x minus I times x plus I. We've found a way to factor x squared plus 1 and find two zeros. It's just those zeros are imaginary. Here again is the first quadratic with its two zeros, 1 and minus 1. We moved it up and got a quadratic with 2 zeros, 1 0 of multiplicity 2. Move it up again, and now we have a quadratic with imaginary zeros. In the late Middle Ages, mathematicians discovered that if one were willing to allow for a new number, one whose square was -1, then quite a lot of mathematics got simpler. They particularly noticed that they could solve quadratic and cubic equations. This so-called imaginary number was therefore very useful. Over time, the term imaginary has stuck, even though scientists and engineers now use complex numbers all the time. It is now common agreement to write I as an entity that satisfies this equation, I squared is -1. Modern cell phone signals rely on sophisticated signal analysis that requires complex numbers. We would not have cell phones or the modern technology with them without the mathematics of complex numbers. Analysis of electrical wiring and electrical signaling uses complex numbers. Complex numbers appear throughout all of mathematics and greatly simplify many mathematical problems. In the next presentation, we will look at complex numbers and quadratic equations.